We're now going to talk about physical and conceptual models, identifying atoms using a spectroscope, the quantum hypothesis, electron waves, and the shell model. So there are various types of models that you can work with. There is a physical model, which is basically an upscaled or downscaled version of the real thing. So if we were looking at a physical model of a house, it would be basically a duplicate of the house with all the rooms built just like they are in the house, only scaled down or scaled up. Conceptual models are slightly different. Conceptual models aren't duplicates of the real thing, but they have parts of it that help you understand what's going on. So, for example, when you look at a football game going on a field and they're talking about, and this is where you'll go, or this is who you'll tackle, they don't put little men like Barbie dolls and have them tackling each other. They put X's and O's. It simplifies the picture, and you can still understand who goes where, but it isn't an exact replication of what's going to actually take place, which would be a lot more difficult to predict and to plan. In chemistry, there are a lot of things that are so complicated that the physical model would be probably overwhelming and perhaps very difficult to create. And so we at times work with conceptual models that take one piece of what we're looking at and present it in a way that we can understand that one piece. So we'll be working with both of these as we go through the course. So your atoms are smaller than the wavelength of visible light. What that means is if you try to look at an atom, you can't see it because it's smaller than what we use to see things with. But we can test out concepts about them and build conceptual models of what we discover. The atom is still being studied and understood. We've figured out a lot of it, but not all of it. There are things that the particles do that we still don't understand. For example, we can take very small particles that make up atoms, and they'll have matching spins. One will be spinning up, one will be spinning down. We can separate them to infinity so they don't even feel each other's presence, and we can flip one and the other one, no matter how far away it is, will automatically flip. We don't understand why it works that way. There are things like that we're still exploring, that we don't have all the answers to, but we are figuring out some of the answers. So we'll look at some of the ones that we do know. The conceptual models we learn in this class won't be duplicates of the actual atom because we're still understanding the atom. And they don't explain everything about the atom's behavior, but they do explain parts, and so they are worth still learning. There is an instrument that we use in chemistry, and they'll also use it in several of the other science courses, called a spectroscope. And it works kind of like when you hold up a prism to sunlight. You hold up that prism there and it separates the light, the visible light, and you see a full rainbow spectrum. If you take an element and you excite the electrons, which are the negative charges around the nucleus, to levels that are higher than their normal ones, they jump back down to their normal ones as they relax, and when they do, they emit light. So if we take an atom and we excite the electrons and watch as they jump back down, we will get our prism showing up with a rainbow, but it just shows discrete lines in the rainbow. And those discrete lines show those energy jumps that the electrons are taking going back. So, for example, if you take sodium and you heat it up, it has this one band in the visible that's very yellow, and you'll see this big yellow line when you look through a spectroscope. Hydrogen has a blue line that you see really strong when you look through a spectroscope. So you've noticed these before because they actually use the light that comes off for your neon signs at times. That's just taking an element and exciting it and letting it come back down, and then you get this beautiful light coming off. So neon signs are red. That's one of the main colors that comes in the visible spectrum for neon when you excite the electrons. Sodium street lamps are yellow because that's one of its main colors that shows up. And you have a lot of fluorescent lights that use this same sort of thing. You'll notice your fluorescent lights that have not been made to be soft white light, which they do by adding other colors using other elements. Those often give you kind of a sickly look when you look in the mirror. That's why some people are like, I'm not switching to fluorescence. And that's because it's not giving you the full rainbow. It's giving you specific things that are excited by what is in that fluorescent bulb. So these discrete frequencies of light act as a fingerprint for each type of element. So each element gives off a unique and characteristic set of frequencies depending on which type of atom it is and what those energy gaps are as it jumps up and then emits light as it goes back down. So here's some various ways we can do it. If you have white light like that comes from our sun, you run it through a spectroscope, you're going to get the full rainbow. If you heat up a gas, say, or you burn an element so that it's also heated up, that sort of thing, and you run it through a spectroscope, you'll get characteristic lines. The one off to the right here is what they get when they do hydrogen. If you instead take a white light source and let it run through something that will absorb some light, let's say we had a large ball of hydrogen gas here, this large white vapor, and we had white light behind it, well, it would absorb in the same energies it emits in because that would allow the electron to jump. And so if you did that, then you would notice that the lines that would normally be emitted are the ones that are absorbed. And so you see the full rainbow except for the heated gas. Now this is really useful for astronomers because they can look at a planet or a sun that's located at a large distance and they can find out the elements that are there by what light is either given off by the sun or what light is absorbed by something on a planet or an asteroid or something like that. And the lines that are missing or the lines that appear tell them what types of elements are found in that particular sun or planet. We use the same thing just to identify elements as well. In fact, this is how they found the noble gases. Since they don't react, they excited them and they saw this rainbow and they realized that they had a particular element that they hadn't done this to before. And that's how they knew that they'd found the noble gases. So the quantum hypothesis. This was presented by Max Planck, who lived from 1858 to 1947. And his idea was that light consists of discrete energy packets. So if a piece of light doesn't have enough energy to do what you're trying to do, it doesn't matter how many pieces of light you throw at what you're trying to do, it will never happen because it comes as a distinct packet and you can't make the energy go up by adding more if it isn't already high enough. But if it's over the amount of energy you need, you can just keep adding light and it'll keep doing whatever you're trying to do. So he called each packet a quantum. It was this section of energy that you were getting from the light. Einstein recognized that these quantum, because they were discrete and you couldn't just like push them all together to make more, they were tiny pieces of matter, smaller than we can see, but he called those tiny pieces of matter photons. So this becomes really interesting because if light has properties of matter, then perhaps matter has properties of light. So the frequencies of light emitted by an element are in these discrete energies, and when they're excited, they would go to one of these specific energy levels and move back down. And when the electron moves back down, it's emitting this energy that we see as light. And they said that those energies have principal quantum numbers. So they'll say if it jumps from 1 to 2, that energy gap is going to be the energy of the light that you see come off. And as it jumps from 1 to 3, that energy difference is the light that you'll see. If it jumps from 2 to 3, that's an energy difference you can see. Now keep in mind, we don't see all those energy differences. We only see them if the energy difference is invisible. But you could detect them with something that detects something like infrared or other energies other than visible. But we will see the ones that fall into the visible spectrum. And what this did is it gave us the planetary model of an atom. We have the nucleus at the center, and we have orbitals that go around at various energy levels, and your electrons can jump out and they can jump back in. They don't actually fall all the way down to the nucleus, but they do move between these orbitals. Now, this right here is a conceptual model because in reality, electrons don't move in 2D, they're 3D. They move all over the place, but they do have areas of energy where they can jump to and from, kind of like these rings that we see here. So they find that you never find an electron between the orbitals, they just instantaneously appear in the next one. And the reason for that is because they have wave properties. If you've ever taken a jump rope and made it go around and then done double dutch and made it go around so that you have 2 loops in that jump rope, if you do it just right so that that keeps going, you'll notice in the middle of the jump rope doesn't move. And the same thing happens with our electrons. We have areas where they're moving, but because of their wave properties, there will be places that they will never exist. They call those nodes. Light has properties of both waves and matter, and it turns out electrons do too. So electrons have wave properties, and because they have wave properties, they're smaller than light, and we can use them to show the same sort of properties that we would show with light. So just as we take light and shine it on something and we see the object, we can take electrons and shine them on things and read what we see and get pictures. And the detail can just be incredible because of electron waves are something that will give a lot more detail than you would get from visible light. So here are 2 electron microscope pictures where they've used an electron just like we use visible light. And you see here a spider and all the detail that they're able to see using electrons. And then they have a piece of hair. We think hair is all smooth, but you take an electron microscope and look at it, and it's actually quite rough on the outside. So your electron moves at the speed of about 2 million meters per second and shows many of the properties of a wave. The wave character of an electron explains why they're only found at discrete levels, because as I was saying, when you have a wave, those electrons will have places where they have nodes, just like your jump rope does when you're doing double dutch. It's got a place where it just isn't ever found. And because they're in 3D, the actual orbitals don't look like those rings that we're using. We just use that because that's very simple for us to think of. They actually look like spheres or like kind of a dumbbell shape. Sometimes they look more like a flower. There's a wide variety of what you find. They've actually categorized them as S, P, D, and F orbital types, and each one has successively more nodes in them and become more complicated. But those waves that are formed have to be self-reinforcing. So if you've ever turned a jump rope with a small child who's never learned to turn a jump rope, you can turn it right on your end, but if they don't know what they're doing, the rope just kind of lies there limply with what you guys are doing on the ends. It has to actually reinforce. You have to get it turning so that you get either 1 loop or 2 loops. And if you're really good, you can try to get 3 loops in there. But there's only specific ways of turning that will give you a jump rope that will move beautifully for you. And the same exists with the waves that an electron makes. There are only specific ways it can move that will allow it to maintain its wave properties. And so because of that, even though we've got this nucleus that's full of positive charges, electrons are negatively charged and they are attracted to positive charges, they will never just zoom right to the middle and stick. They have to instead orbit around to keep their wave function going. And so they never actually collapse down into the atom. And that's a good thing. It would be a bad thing if they could collapse down, because you would totally lose your atom, because they're what make the actual circumference of an atom. So the smallest orbit can be no smaller than a single wavelength of an electron. And that's why it never goes to one pinpoint in the center. So we have this shell model that we describe an atom by. It has 7 concentric shells around the nucleus. Shell 1 holds 2 electrons, and it's just period 1. So if you look at your periodic table, you'll notice that you just have hydrogen and helium, and those 2 elements correspond to the fact that shell 1 can only have 2 electrons. So hydrogen has 1 electron, helium has 2, and then we move down to period 2, which is going to have shell 2. And that can hold 8 electrons. And if you count across the periodic table, you'll see there are 8 elements successively having more electrons. So that period starts with the 2 of helium, and then you get 3, 4, 5, and it counts across till you get to 10. Shell 3 holds 8, shells 4 and 5 hold 18, and 6 and 7 hold 32 electrons. And so if you count the elements that are in the periods that correspond to those shells, you'll notice that you have 18 going across 4, 18 going across 5, 32 for 6, 32 for 7. Keep in mind, those bottom actinide and lanthanide series are within your periodic table, and so that's how you get your 32. And they start filling up at the very middle, because those are the ones closest to the nucleus. Negative charges are attracted to positive charges, so they'll get as close as they can. And then as you add more electrons, they fill out going out. As areas fill up, you can't add any more electrons, and so they have to move further from the nucleus they're attracted to. So each element has the same number of electrons as protons. So the overall plus and minus charges, if you were to add them up, you'd get 0, because you have the same number of plus as you have minus. So for example, hydrogen has atomic number 1. That means it has 1 proton, so 1 positive charge. So to balance that out, it's going to need 1 negative charge. So until we start doing chemical reactions, and I'll tell you what to do when we get there, the number of electrons an element has matches the atomic number, which is the number of protons it has. So lithium has the atomic number of 3. That means it also has 3 electrons as well as 3 protons. 2 of those electrons are going to be located in shell 1, which only holds 2. But then the next one has to move to shell 2. So shell 1 has 2, shell 2 has 1, and that's where its 3 electrons go. To the right, you'll see the shell model for sodium. You'll notice that shell 1, that inner ring, has 2 electrons. That's as much as it can hold. But sodium has more electrons than 2. And so if we go to shell 2, that one can hold 8. And if you count the dots, you'll see that there are 8 there. And then shell 3, we're going to put 1 more in, because sodium's atomic number is 11. So we need to be able to put 11 electrons around the sodium nucleus. Now that outer ring is called your valence ring. And your valence ring contains valence electrons. Those are the electrons that will participate in chemical reactions. The inner ones just sit there. They generally don't participate in chemical reactions. So sodium has 1 electron to do chemical reactions with, and the other ones just stay in the middle for stability.